Patrick Moore, now on BBC Two, presents Studies of the Southern Sky, in another edition of The Sky at Night.
Southern Hemisphere astronomy is particularly significant, if only because some of the most important of all astronomical objects are in the far south of the sky, such as the Clouds of Magellan. One of the first major observatories to be set up in Australia was at Mount Stromlo near Canberra, and there are big telescopes here. The largest is a 74-inch reflector, used, of course, with the latest electronic equipment and concentrating mainly upon spectrographic research. Seeing conditions at Mount Stromlo are not ideal. We are too close to Canberra, but they're good enough for very important research to be carried out, and the 74-inch is in use every clear night. Why was the observatory established in Canberra?
Well, the history of the observatory closely parallels Australian history since Federation. The Australian Constitution prescribes that it is the federal government that should make laws regulating astronomical observations. So within about 10 years of Federation, there was a site testing party out here in the Australian Capital Territory looking for a suitable site for the Commonwealth Solar Observatory.
What telescopes are here now?
There's this largest telescope at Mount Stromlo, the 74-inch reflector. There is a 26-inch refractor, which is used for astrometry. There is the 50-inch reflector.
Had rather a checkered history. What is the story behind it?
Well, it goes back a long way. It goes back to the 1850s, when the Royal Society in London was looking for a suitable site for a large reflector to study nebulae. In the 1860s, the colonial government of Victoria was setting up the Melbourne Observatory and seeking to acquire a large telescope, went to the firm of Grubbs in Ireland and commissioned a large reflecting mirror.
Why was it decided to use a metal mirror?
Astronomy is always at the forefront of technology, and at the forefront of technology at the time was metal mirrors.
It's often said that in its original form, the great Melbourne reflector wasn't a success. Is that true?
It had problems. The metal mirror, of course, expanded and contracted with changes in diurnal temperature, and so there were aberration problems. But it's said that on fine nights, it gave good images. Of course, fine nights were defined as those with good images.
But after a few decades, it fell into disuse, and then what happened next? It was transferred to Canberra.
In 1944, the telescope was moved to the Commonwealth Solar Observatory and was completely refurbished with a Pyrex, that is a glass spherical mirror, and set to work on astrophysical observations.
In its modern form, the great Melbourne reflector at Mount Stromlo is involved in a fascinating project, the search for MACHOs, massive astronomical compact halo objects.
MACHOs are a kind of object which have been hypothesized to be the dominant form of dark matter that astronomers are looking for to explain the internal motions of galaxies, and indeed cosmologically perhaps to close the universe through the gravitational force of massive hidden matter, dark matter.
How do you tell a MACHO event when you find it?
Well, we are monitoring the many millions of stars in the Large Magellanic Cloud. Most of those stars will have quite constant light curves. They'll be quite normal everyday objects. Some of them will be periodic variables, but occasionally we will see, and we expect a rate of 1 MACHO event per 2 million stars, that we will see this characteristic brightening of a star, a background star, as it's gravitationally lensed. We will see a constant light curve for many days, many weeks, many months, and then suddenly a brightening, which is symmetrical. It'll go up just as quickly as it comes down, and also it will be the same in any colour we measure, and we are measuring in 2 colours, blue and red.
There's a great deal of missing mass in the universe. Do you think MASHO is going to account for that?
We have discovered one, and we have several other quite strong candidates after having observed roughly 5 million stars. So it appears that the MACHO frequency could account for the internal motions of our galaxy.
How big and how massive are MASHOs, do you think?
The MACHO objects could, of course, be of any size, from very small masses up to many solar masses. But in terms of the experiment we're doing, the MACHO objects are most easily discovered having masses between something of planetary size, Jupiter, Saturn type size, all the way up to several solar masses. This is what's within the scope of this experiment that depends on gravitational lensing by these MACHO objects of background starlight.
You've examined 5 million stars so far. How many stars do you think you'll examine by the end of the program?
About twice that. But we'll have many, many more points on the light curves of those stars. So the data flux through the telescope is quite enormous. There's more data being collected on the Magellanic Clouds in the last 15 months with this telescope than has ever been gotten on that system before.
Mount Stromlo's closeness to Canberra made it necessary to find a better site. Well, there are no high mountains in Australia, but conditions here at Siding Spring are pretty good. There are no towns close by, and the nearest town of any size, Coonabarabran, isn't very big. The observatory is very accessible. You haven't got to climb a volcano or battle your way across hundreds of miles of desert. This is the dome of the Great Anglo-Australian Telescope, or AAT, one of the most efficient and most powerful in the Southern Hemisphere. It has a 153-inch mirror, and of course it's fully computerized, although unusually it can also be used for photography. It's been in operation now for around 20 years.
It's an extremely versatile telescope because we have a very wide range of sophisticated different pieces of equipment for doing different kinds of astronomy. And what happens is that every few nights a different crew of astronomers turns up to use the telescope for their work. And so, for example, at one end of the universe, if you like, we're doing cosmological work, observational cosmology, plotting out the positions and the distances to the most distant galaxies and quasars to try to understand the really large-scale structure of the universe. At the other extreme, we have people working on objects in the solar system and using the infrared camera, for example, to look at Venus, or looking at stars, nearby stars, which may have planets going around them, and so on.
The use of fiber optics is becoming very important in astronomy. What developments are you working on here?
We've done a great deal of work over the years. In fact, we were one of the first telescopes to use fiber optics, the point being that you can then collect the light. Instead of looking at one star at a time or one galaxy at a time, you can look at 50 or 100 stars simultaneously, which means that you're just that much more efficient by putting the light from each object down a separate fiber. But not content with that, we decided we'd go one better, and we're right now building a new system called the 2-degree field. And that will give us a field of view of 2 degrees, as it said, at the prime focus of the telescope, which is by far the widest angle, largest field of view of any big optical telescope. And in that field, we're going to put 400 fibers. And so it's another, if you like, another factor of 10 increase in the power of the telescope. So in future, we'll be able to measure the redshifts of 400 galaxies every half an hour. So thousands of galaxies per night.
The AAT is much the largest telescope here. What about the other telescopes on Siding Spring?
The next largest telescope here is the 2.3-meter telescope of the Australian National University, the Mount Stromlo astronomers. And that's a more recent telescope than ours, a little bit smaller, but built to modern design principles. And then they have 2 or 3 smaller telescopes. The other telescope that we at the Anglo-Australian Observatory are particularly involved in is the UK Schmidt telescope, which was originally built and operated by the British as an outstation from the Royal Observatory, Edinburgh, but which has now become part of the Anglo-Australian Observatory.
Beta Pictoris is one of the most interesting stars in the sky. It doesn't look very bright, but we know that it's surrounded by what appears to be a protoplanetary cloud.
What we are able to do is monitor the velocities and the abundances of the material that is falling onto the star. So we can actually see comets, in fact, leaving the disk and evaporating as they approach the star. And with this very high resolution, we are able to study this phenomenon in much greater detail than ever before.
Do you think this cloud will in fact develop into a system of planets?
We have to look very hard and prove that what we're seeing are comets, If that is the case, then it is in all likelihood going to develop into some sort of planetary system. Whether it will be like ours, where life can form or not, is another question altogether, of course.
The AAT is also very valuable in the infrared range, and a great deal of infrared research is carried out with it.
It was never designed for infrared work. It was designed as an optical telescope, and there are certain things you should do to make one work well for the infrared. We've succeeded because of the instrumentation we put at the bottom. We've made wonderful instruments, and we've been able to overcome the difficulties of the telescope and the fact that the sight is not ideal. And that's really why we've done so well for infrared work. It's the instruments.
What have you been concentrating on lately?
One is the centre of the galaxy. Now, we'd love to know what's going on in the centre of our galaxy, but we can't see through all the smog, if you like, the dust and dirt through the galaxy at optical wavelengths. So you have to work in the infrared, where you actually get the transmission through. And at the centre, you'd expect there to be huge numbers of old, cool stars. But in fact, what we found is that there is a mixture of old stars and some quite young ones, sort of a few million years old. And most of the energy that's coming out of the galactic centre is produced by these enormously bright young stars, which is something of a surprise to people. And we can now put everything together. We can see why there's gas there that's in the state it's in, and so on. We don't understand yet why the stars are there. Second thing I've been looking at is the planet Venus. Now, one tends to think that Venus is not of much interest because it's covered with these great thick layers of clouds and you can't see through. But in fact, we've found that by using infrared radiation, we can see right the way through the clouds, all the way down to the surface. We can see the high plateaus, we can see the plains, not in any great detail, but we can see that they're there. And this enables us to study the atmosphere, which is of great interest. For example, by looking at the lowest bits, the lowest few kilometers, where all the gas and all the excitement is, we can tell how much water vapor is present, which says something about how the greenhouse effect works on Venus. The third thing I'd like to mention is the Orion Nebula. Now, Orion is a region that's been observed almost ad nauseam. It must be one of the most observed places in the sky. Now, recently, quite by chance, I was making pictures of the Orion Nebula, and I bumped into a feature up at the northern end, just above the infrared group, which had been vaguely known about, but had not been seen in much detail. And what we now see is that there's been some massive sort of explosion, where blobs of gas have been thrown out into the northern part of the nebula. And behind each one there's a sort of wake. It's like a boat going through water, which is something visible in a different type of light, different molecular light. It's the hydrogen itself. And we've never seen anything like this before. And it's set people thinking, it's really turned everything upside down on star formation, on what happens with massive stars, because nobody had expected anything like this.
I've said that it's unusual for a modern telescope to be used for traditional photography. Dr. David Malin is the photographic expert, and his pictures of nebulae and galaxies are in a class of their own. But there's nothing traditional about his photography.
Many people are taking pictures with charge-coupled devices, electronic detectors. But at the Anglo-Australian Observatory, we've maintained a photographic capability for a variety of reasons. We can certainly do good science with photography. It's very important that we have the wide field capability. But also we operate the UK Schmidt telescope, which is basically a photographic instrument. And so having a photographic capability in the whole organisation is still extremely important to us, especially when we want to study the very large objects that we can see in the south. For instance, we have the Magellanic Clouds here, most wonderful nearby galaxies. They're perfectly fitted onto a UK Schmidt plate, which is 14 inches square.
What techniques do you use?
Well, I use a range of techniques. Amongst them is a technique I've devised called photographic amplification. It's a simple contact copying process which extracts the faint images from the photographic plate and produces a very thin-looking film positive of the plate. But then I can add together large numbers of those thin film derivatives and combine the information to produce much, much deeper images than you can obtain from a single plate alone.
What have been your latest results?
We've been copying large numbers of plates and combining the results together, and we've been manipulating pictures of nearby bright galaxies, galaxies that are well known and well studied. And these are beginning to show extraordinarily large and very puzzling extensions, very faint outer features that are very difficult to explain. I think they're giving us a handle on the dark matter. We're beginning to not see dark matter, but see the effects of dark matter on the outskirts of galaxies. And that's interesting and important that it's being done from archival material.
I imagine you work very closely with other observatories.
Yes, indeed. As well as my colleagues here at the Anglo-Australian Observatory, I've worked on La Palma. Indeed, recently we took some pictures on the Isaac Newton telescope on La Palma. The first time this has been done photographically for many years. I have collaborations with observatories all around the world working on various projects, all of them, most of them anyway, with some relationship to photography.
Yet there are some things that even the AAT and the UK Schmidt can't do. Remember, a star is so far away that it looks only like a dot of light. But in Australia, a new piece of equipment has been designed and built which will, for some purposes, be equivalent to a 640-metre telescope. It's called SUSI, the Sydney University Stellar Interferometer, and it's been set up at Narrabri, some way north of Siding Spring.
Well, SUSI is a new instrument for measuring stars, for measuring the angular sizes of stars. And when we talk about angular sizes, we mean, in fact, if you like, the angle between lines drawn from the Earth to the two sides of the star. This is an incredibly small angle. The largest star in the sky, if we measure its angular size, is equivalent to measuring the diameter of a human hair at a distance of 100 meters. That's an incredibly small angle. Now, if you look through even the largest optical telescopes that we have today, most stars appear just as points, just as they do to our naked eye. But there are only 6 stars that we can see as disks, so we could actually measure their size with a telescope. To measure more stars, we need a telescope with a mirror 10 meters, even hundreds of meters in diameter. And of course, it's quite impossible to build a telescope with a mirror hundreds of meters in diameter. So what we do is we use an interferometer. And in an interferometer, what we have are a number of small apertures. And we can combine 2 apertures at once. In other words, we bring the light from 2 small mirrors in together, combine them in the appropriate way, just as they would in the main telescope. And by making a series of measurements with different separations, we can, in fact, build up the same angular picture as we would get with a big telescope. And here in SUSI, we have baselines, as we call them, or separations, which range from 5 meters right the way up to 640 meters.
When you can measure the diameter of a star, obviously it tells you a great deal about the star's makeup.
That's exactly right. And in fact, the measurements that we make with SUSI will be combined with measurements made with conventional telescopes, the photometry, which is measures of the brightness in different wavelength bands, different colors, and also measurements made with spectroscopes. In other words, measuring the distribution of light through the spectrum and the way it changes. For example, when you look at a binary star and you're looking at the 2 stars orbiting around one another under their mutual gravitational attraction, you see changes in the spectrum. And by combining information from them with measurements from SUSI, we can determine the energy actually coming out of a square meter or square foot, if you like, on the surface of a star. That tells us the temperature of the surface of the star.
What about pulsating stars, such as the all-important Cepheids? Are you going to be able to measure their changes in diameter?
Yes, in fact, that's one of the more exciting programs that we plan to carry out, and that is to actually measure the angular variation. And then by combining it with the spectroscopic measurements, we can in fact determine how far away they are. And because they're such a fundamental calibration step in the distance scale of the universe, we're going to be able to provide a completely independent calibration, which is essentially a geometrical one. And I think this is a very exciting program.
How is the light collected?
Well, we have input mirrors, steerable input mirrors, which are called siderostats, and they reflect light into an evacuated pipe, which brings the light right along the baseline, as we call it, into the central building, and it actually enters the building over here. The first thing that happens is that we reduce the size of the beams down to 50 millimeters, about 2 inches across, just for convenience. But then we have a problem, because the light coming into our 2 stations, in fact, is traveling different distances. It arrives at one station before the other. The paths have to be matched very accurately to a few millionths of an inch. And in order to do that, it means that we have to have a variable path inside the instrument. And over here, you can see a carriage which moves up and down between the 2 beams, and it moves continuously, because the path difference is changing as the Earth rotates. It moves continuously through an observation to keep the paths exactly equal. And that perhaps is the most crucial part of the whole instrument.
When will SUSI be fully operating?
Well, as far as the scientific program is concerned, we have actually started, and so from that point of view, as far as baselines up to 80 meters we are now really in operation, it'll take another year or so to bring all the baselines out to the full 640 meters into operation.
So there's a great deal going on in Australia. But there are some places in the world that are better as astronomical sites. Mauna Kea in Hawaii is one, and the Atacama Desert in Chile is another. Luckily, there's an area not too far geographically from Australia which can be used, and this is the South Pole. It's been imaged by the Galileo spacecraft, and it does look decidedly inhospitable. The conditions near the pole are expected to be very good. The main problem is that it's going to be somewhat chilly.
It's the combination of the extreme cold, the very dry conditions, and the tenuous air, which makes it a fantastic place for doing astronomy. The cold weather makes the thermal radiation, what we call heat, much reduced. So anyone doing infrared observations automatically gets far more sensitive data. The very dry conditions mean that the transmission through the atmosphere is considerably improved from anywhere else on the planet. And the very stable air means that what we call the seeing or the twinkling of the stars is considerably reduced from any other site. And this combination of dry, cold, and stable conditions is going to make the Antarctic Plateau the ultimate place for doing ground-based astronomy.
Will the intense cold be a hazard?
Hazard's probably not the right word, but it's certainly going to be a challenging thing to overcome. I regard it as really an engineering problem. We certainly believe it's a great place to do astronomy, but it's going to be very difficult. And operating at up to minus 90 degrees below zero, which is the coldest wintertime temperature, is going to be a great challenge for us.
One thing strikes me. Down at the South Pole, you have a 6-month-long night. Is that going to be an advantage, a disadvantage, or both?
Well, in fact, the last one is both. It's certainly going to help some observations. It's going to hinder others. Some optical observations like very long time period observations, and a 6-month night will help that. Of course, it means you can only operate in the winter. You couldn't operate in the summer. But the astronomers who are going to gain most from the possibility for long, continuous observations are the radio astronomers. Radio astronomy, it doesn't matter whether it's night or day. As long as you can see your source in the sky, then you can observe it and measure it. And so from the South Pole, anything you can see, you can of course see all the time. The source doesn't set on the horizon. So you could do long, continuous measurements.
Environmentally, Antarctica is unique. Are the environmentalists worried about astronomical activity there?
Well, they're right to be concerned, and we're concerned ourselves. Antarctica is certainly a fragile ecosystem, and it's one we don't want to disturb. But astronomy, in fact, of course, is one of the most peaceful operations you could have. We're essentially a passive activity. All we're doing is looking at the night sky, detecting the photons falling upon the telescope. And so once the observatory is set up, our impact will be minimal. But you're right to express those concerns. We already have started talking to organizations like Greenpeace to find out what kind of concerns and objections they might have. But environmentalists also, they're keen to work with responsible people too.
Well, that lies in the future. But I hope that in the foreseeable future, we'll be able to present a Sky at Night program from the South Pole. But meanwhile, there's plenty to occupy our attention. Southern Hemisphere astronomy is now of paramount importance. And in all this work, as we've seen, Australia has contributed a tremendous amount. If you like a copy of our latest newsletter, then send your stamped address envelope to newsletter number 53, The Sky at Night, BBC Television, London W12 7RJ.